Hello and welcome to this next lecture on fundamentals of acoustics. Today we will look at branched systems. Branched pipe systems. Okay. So what is a branched pipe system? We have a pipe, let us say, of a certain cross section S, and there is an incident pressure A e to the power of minus I k x, and let us say the junction, there is a junction where it branches, and let us say this is the origin of sorts, and this cross section is, let us say, S1. Okay. So that we have a wave P1 e to the power of minus jk x1 going that way, and this cross section, let us say, is S2, and we have P2 e to the power of minus jk x2 going this way. So the okay, so now because this A is incident on a junction, there will be an impedance change, so there is a reflection. That reflection is B e to the power of I k x. So there are three unknowns. B is an unknown, P1 is an unknown, P2 is an unknown. Okay. So what are the conditions? We need conditions or continuity conditions to solve this. So at x equal to 0 or at the junction, A plus B must be equal to the pressure there, from either of the pipes as you come towards the origin or junction. The other is the volume velocity. We have to see continued volume velocity because now the pipe cross sections are different. Okay. So that means what? The QA, volume velocity due to wave A, plus QB, volume velocity due to B, must be equal to Q1 plus Q2. Okay, note the difference here. So we have, this is one condition, this is another condition 2, and this is the third condition. We have three unknowns. Okay. So let us see now, QA plus QB by P1 by A plus B. Okay. So QA plus QB divided by A plus B is equal to Q1 by P1 plus Q2 by P2. Okay. P1 is equal to P2, that is why we can write this. Okay. Now what we say here is that P1 by Q1, this is pressure over volume velocity. This is called the acoustic impedance. Okay. Pressure over velocity is specific acoustic impedance. So far I have been addressing that only, but not mentioning it every time. So pressure or volume velocity is actually the acoustic impedance as it is mentioned in textbooks. Okay. So now QA plus QB is the volume velocity, which is what? Particle velocity due to A particle velocity due to B into the cross section area. Okay. So, S divided by rho 0 C A minus B. So, if we use this over here, what do we get? We get S into A minus B by rho 0 C into A plus B is equal to, now what we will do, okay, what I am saying is that we have 3 equations, we can solve for B, P1, P2. Okay. So, that is not a big problem, it is just a linear algebra problem. What I am going to specifically do here is that I am going to think of a system like this, okay, where P2 moves towards the right, let us say to infinity, it has the same cross section S, and here we have the same cross section S, and we have A coming in and B going out. This is an x equal to 0 junction, let us say, and looking this way we have ZB a certain acoustic impedance. This is like the P1 branch. Acoustic impedance here is ZB. Okay. So, this is the left side over here. The right side I will write it in terms of acoustic impedance of the branch, which is 1 over ZB, and that of this is the same, which is S by rho 0 C. Okay. Specific acoustic impedance is rho 0 C, divided by S is acoustic impedance of a straight pipe. Okay. So, now this being the case, from here A minus B by A plus B happens to be rho 0 C by S ZB plus 1. Okay. From here we can get B by A, the reflection coefficient, as minus rho 0 C by rho 0 C. Okay, hold on. Minus rho 0 C by 2S by rho 0 C by 2S plus a ZB. Okay. And the pressure P2 by A in the pipe going straight down is found from what? A plus B is equal to P2. So, that P2 by A is 1 plus B by A. Okay. So, using B by A, P2 by A is equal to ZB by rho 0 C by 2S plus ZB. Okay. Now, this is a very nice result over here, because if in let us say earth moving equipment, like bulldozers and so forth, okay, the entire job is done through hydraulic pressure. Okay. There is a pump, gear pump or something. It is connected with a line, a high pressurized line. You can have pressures as high as 3000 psi, and then there are some valves over here, okay, metering valves, and then pipes go and they are connected to a bucket, hydraulic a bucket, okay, for earth moving. Okay. Now this gears are rotating, and so they are sending in pulses. So there is a mean pressure of 3000 psi, let us say, and then there are pulses on top of it. Now it may just happen that the line length and all the properties of the oil and air trapped in it are such that this line goes into resonance. Okay, acoustic resonance. So what happens is there will be pulsations on top of 3000 psi, and these can be very high. Okay, so the pressure now can oscillate like this in the pipe. Okay, this may even reach 3000 psi, which is dangerous, because 3000 minus 3000 goes to 0, etc. Okay, so you will have boiling and all that, cavitation. So now, so these are typically quite high when the resonance hits, and so what happens is that here the metering valves will start oscillating and the bucket starts to oscillate. Okay, so this can become very dangerous. So now this is the same system as we have here. Okay, here we have P2, here we have A incident and B reflected. Okay, now what we do is we put in a side branch. We put in a side branch with an impedance ZB. That is what we have done so far, and that has given us what? The pressure here, oscillating pressure here divided by A, incident pressure as this, as a function of this ZB. Okay, and let us say this is a pipe with closed end. Then we know that the impedance is minus J rho 0 C cot KL. This is specific acoustic impedance. Okay. Now with this being another cross section, whatever it is, it will be SB. Okay. So this part is less important. Now I can choose my KL, that is frequency and speed of sound and the length I can choose such that cot KL goes to 0. Okay, there is not a significant choice with respect to K, okay, because that is a certain frequency where oscillations are happening, but you can adjust your length such that cot KL goes to 0 or ZB goes to 0. If that happens, then P2 over A can go to 0. So here you can have 0 pressure. So you suppress the oscillations. Okay. So this is called the side branch resonator. Okay. By setting cot KL to 0, the side branch is resonating. As a result, its impedance drops, so that the input pressure dominantly interacts with it and the pulsations downstream are 0. Okay. So this impedance is higher, so the input pressure interacts with the low impedance side and this side is left alone and the pressure pulsations are 0. So these are very good solutions for this kind of a problem. Okay. Just as a just as a calculation, if ZB happens to be RB plus JXB, okay, then the power reflection coefficient turns out to be B by A whole squared is equal to rho 0 C over 2S whole squared by rho 0 C by 2S plus RB whole squared plus XB squared. And the power transmission coefficient, which is P2 by A whole squared, is equal to RB square plus XB square by rho 0 C by 2S plus RB whole squared plus XB squared. Okay. So, if both RB and XB go to 0, RB is typically very small, okay, and XB go to 0, then power transmitted is 0, power transmitted downstream is 0. Okay. So, that is one applied problem. Now, let us look at another problem over here. Okay. The other problem is this. It is called the Helmholtz resonator. Okay. It looks like this. There is a neck, and there is a bulb of acoustic fluid. There is a short neck, okay, of length L, and this has a nominal volume B 0, okay, and this has a cross section of S, okay, and this is a volume of constant mass. So, rho, let us say V is a constant, okay, then delta rho V plus delta V rho is a 0, okay. So, that delta rho by some nominal value rho 0 is equal to minus delta V by B 0, okay, and this delta rho is perturbed density. So, we will say rho dash is equal to minus rho 0 delta V by V 0. Now, what is delta V by V 0? Suppose I give it a slight movement over here, apply a pressure and let it move in by an amount xi, then the cross section into the movement is the volume change. So, this is the volume change delta V negative, okay. So, now if I use that minus rho 0 minus S xi by V 0, so that is equal to rho 0 S xi by V 0, okay. Now, we know that rho dash C square is acoustic pressure, okay. So, that means what? The acoustic pressure P dash is rho 0 S xi B 0 C square, okay. And what is the force? Force is into S. So, the force is equal to P dash into S is equal to rho 0 C square S by V 0 into xi, the movement inward movement. Okay. So, this is the force. Now, force over displacement, xi is equal to rho 0 C square S by B0, this is the stiffness of the system. Okay. And now the mass of the neck, is how much? We have S, the cross section, L, the length, the volume, and rho 0. This is the mass of this section. Okay. Now let me show you one thing here, is that the specific acoustic impedance is pressure over particle velocity for a piston driven rigid ended tube is minus J rho 0 C cot KL. Okay, minus J rho 0 C cot of KL is equal to minus J rho 0 C cos of KL by sine of KL. Okay, KL is equal to twice pi by lambda into L. So if KL goes down, if KL value goes down, reduced, that means L is small compared to lambda. Okay, so this is a short tube. If it's a short tube, okay, under such conditions we get minus J rho 0 C cos KL approaches 1, whereas sin KL approaches KL. Okay. Now we have minus J rho 0 C 1 by omega into C L is equal to minus J by omega rho 0 C square by L. So this is a stiffness with a stiffness value rho 0 C square by L. So short tube, okay, in comparison to the wavelength which is rigid ended, behaves like a spring. Okay, or a closed ended volume which is somewhat smaller in its measure than a wavelength, behaves like a spring. Okay, so now this, in the Helmholtz resonator case, this is the bulb that is behaving like a spring and it has this stiffness. Similarly, if we have an open-ended pipe, okay, we have a pipe that is open-ended and again piston driven, we know that the specific acoustic impedance is given by plus J rho 0 C tan KL. Okay, and it's open ended, that means pressure at the end is 0. So if we have pressure over particle velocity given by J rho 0 C tan KL, and we do the same thing, approach low frequency, so that KL tends to a small value, then we have this as J rho 0 C sin KL approaches KL cos KL approaches 1. Now I have J rho 0 C, K is omega by C into L. Okay, so I have J, let me just see here. We need a force over velocity, so this is P over velocity, so into S is S, sorry, this has stiffness units. Okay, there is a spring with this stiffness. We need a cross section area to make it a force. Okay. Okay. Now same thing here, we will multiply by a cross section. So, we will have a cross section. Okay. So, then what happens? Then we have j omega into rho 0 into SL. SL is the volume of the pipe, rho 0 is the mass of air in the pipe. Okay. So, now this is j omega times mass of air in the pipe. So, that means an open ended pipe from the driver position looks like a mass. Okay. And the value of the mass is the volume of air in the pipe. Okay. So, why I did this is that in the case of the Helmholtz resonator, we have a short pipe, okay, and a bulb of air. So, this short pipe now behaves like a mass because it is open on both ends, and this closed bulb behaves like a spring. Okay, and those values we found. So, this is the value of the spring constant rho 0 c square S by V 0. So, it's a spring constant is rho 0 c square S square by V 0, and the mass in the neck is rho 0 SL. So, if you take the square root of the spring constant, divided by mass, it is like square root of k by m in the vibrations case. So, we get a square root of rho 0 c square S square by V 0 rho 0 SL. Okay. So, this ends up as c square root of S over V 0 L, okay, in radians per second. So, this happens to be the natural frequency of the system. Okay. Now, if there is a room where there is an offending frequency omega n, okay, if we can put in a tuned Helmholtz resonator, okay, this is typically small in dimensions, okay, I am just exaggerating, and you tune the S and V0 and the L values so that the resonant frequency of the Helmholtz resonator is omega n, then you will be amazed that a lot of interaction will happen close or in the Helmholtz resonator. The sound field will very heavily interact with the Helmholtz resonator because the impedance it sees is 0, and the rest of the room will be quiet. Okay. So, it is like a passive quietening device, okay, passive noise control device. Okay. I will close this lecture here now, and we will continue from here in the next class. Thank you.